we're Trustworthy Bridges. I'm Mallow, and this is Lauren. So we're going to talk about our design brief. So we had to make a bridge that was under $300,000 approximately, something that's affordable. And it had to be strong enough to hold a truck. And it had to have a concrete deck that could sustain its weight and be aesthetically pleasing to the eye. So, go for it.
Oh. Sorry, I got nervous. Carbon steel. It's metal. It's a combination of two things: iron and carbon, not carbon and steel like many people think. There's other things in it, but there's just a small percentage that they don't even really count because no one really cares about them. There's also different types of carbon steel. Weren't there multiple types on the thing? Yeah, there are multiple types there, but there's low carbon, medium, high carbon, and then very high carbon.
Alright, so compression and tension. So tension is a force stretching a joint, and compression is a force pushing against the joint. So you can see, and this is just a model truss, which members are in tension and in compression. So these are our initial truss designs. We have truss number 1, which I thought was aesthetically pleasing, but Mr. Menjivar told me was not. I think it looks awesome. I don't know why it has to be on the top. Then the second one was just too expensive, but I think it's because the pier was too low. Because that was before I realized that you could change the settings. So then truss number 3 is just a beauty. Look at that. Wow.
It's a nice bridge.
It's a nice bridge. And if you don't believe me now, just wait. So we use this design matrix.
Decision.
Yeah, decision matrix. Used to analyze performance. So we factored in cost, structure, resources, aesthetics, and then we totaled it. And we did it on a 1 to 4 scale. And clearly, number 3 is the greatest of them all. But of course, truss number 1 deserved that too. So, as you can guess, we decided to go with truss number 3. Look how nice it looks. Amazing.
Our bridge is close to both of these. It's modified queen and Belgian because usually bridges have like the members that go either inward or outward, but since ours is aesthetically pleasing, we decided to just go both and make them like zigzag triangles.
Yeah, so you can look at reference. These are these trusses that she had. And then this is the way ours look. So you can see it sort of looks like the modified queen. So this is our cost report. It's the material cost, connection cost, product cost, and site cost. So it only adds up to being $290,692. So below the design constraint, 300,000. These are all our members list. We only have 21 members. All the different lengths. None of them are particularly long. All of them are under 9. These are the low list, which means absolutely nothing to everyone until you see the compression force to strength ratio. So in order to get this ratio, you have to divide the average compression force by the average compressive strength, as well as the tension, and then those numbers don't really mean anything until you see this. 0.18 versus 0.8, which still doesn't mean much unless you know that the truss is only using 18% of its total compression force over strength and only 8% of its total tension force over strength.
So clearly, our truss number 3, best truss out of probably everyone's in this class, no wins. It's quite aesthetically pleasing, not too expensive, just some pocket change. It has both compression, tension, and these are references we used for that's terrible.
So now it is time to show animation. See how beautiful ours is. Zoom in a little bit. And if you wanted to see how it would look if you're in the truck, wow, you see that? Amazing. Wow. So that is our truss. And that that concludes our presentation.
All right, give him a hand.